Hello. Hang on a second. No, that's... Turn that off. Display capture. Maybe this? No. Maybe this? Huh? There we go. Or maybe it's just the display, I'm not sure. I've totally forgotten what I've totally forgotten how to do this. Let's see here. Huh, where's my comments section? Where is my comment section? Can't see everybody. Huh. Live chat. Enabled. Can I enable it? Oh no, why is it disabled? Is this a new setting? What's happened? Oh no. Well, that's unfortunate. Okay. Alright, so everybody run to the Discord, because we can all talk there. I'm sorry that we can't talk on the YouTube thing, because guess what? There is a setting that I didn't know about, and you see here, right here, it says Enable Live Chat. And I've never had to click that before, but you see it's unchecked, and I can't click it now because the video is going on. So I think we just have to settle. Okay. Oh, that you couldn't see that. Looks like everything is screwed up today, and it's all my fault. Yeah, see here, there's an enable live chat, and I did not click that. Okay. Okay, so let's I guess I can even just join main voice and people can talk to me. Your voice won't be on the video or anything, if that's what you're worried about. Okay. So I want to talk about two topics today. Let's create... Well, actually I was thinking we might do a little bit of Python today. Also, is this really doing that? I don't like that. Let's do this instead. Let's see, window capture. Nope, that's not working. Display capture 3. Okay, that's working. Now we turn off that and that. Okay, I think we're getting there. All right, so we're almost ready to begin the class today. You know, so I'm sorry about that. Let's do some announcements. This was me explaining quicksort to the 201 kids. So let's do some announcements. So the most high priority is exam grades. I'm working on it. I'm hoping to have them done maybe today or tomorrow. When exams are in person, when I have them on paper, exam grading takes a short time. But when they're on Blackboard, when on Blackboard, exam grading takes far longer. And I don't know exactly why. I wish I could improve my process, because it seems like I've just become like 100 times less efficient. And I don't know why. It's really annoying. But yeah, I'm just way less efficient when I'm on Blackboard. And, okay, medium priority. Yeah, so if you want to see how your projects were graded, if you go to your submit directory, there's a folder called 00 grade sheets. And in there, there's the rubrics for your projects. Okay. And then, what else? Let's think. Oh, you guys want another homework. I'm going to write one. It's going to be about hash tables and heaps. And I think that's just about it, right? And then the last thing to ask is, how is Project 4 going? Let's see here. Okay. All right, so okay. So, right, let me go back to the data structures thing and just ask you that question. So, yeah, please start your project 4. I don't think it's going to be that hard, but I do think that it's important to start. Try to get the heaps done relatively soon, right? Just so that you can start on the hash table. The hash table is also not hard, but you know how things are in 341. If you don't start early, if you don't start debugging your code, you're going to end up with things that you can't fix. You know, it's not hard, but if you don't start debugging, then you'll end up not finishing. So I don't want a lot of extensions on Project 4, just because A, we're heading towards the end of the semester, and B, I want it to be something that we show everybody that we are capable of doing something on time, on target, okay? Okay, so today I want to talk about two things. So the first thing I want to talk about is I want to talk about disjoint unions, and then I'm going to spend a little time talking about tries. Okay, so those are the two data structures I'm going to cover today. Basically, they're both tree structures in the end, but I want to just talk about them because they're different. They're not heaps, they're not binary search trees, they're not, you know, there's a lot of things that they're not. They're tree structures, but different. So, okay. So I guess let's start talking about disjoint unions. So disjoint unions. Let's begin. Basically, so some books have two operations. I'll just basically, or three operations. I'll just talk about two. I'm going to talk about union, union X and Y, and I'm going to talk about find set X. So basically, let's imagine that we have an array of elements. So we're going to have some kind of array. Oops, that is totally not what I want. All right. Good enough. Let's build an array. Okay, maybe that's good enough. And then what we can do is just take all of these things and space them evenly. Do that, and then move them down. There we go. That's good enough. So basically what we want to do is each one of these is an element. Let's just number them. So we have something like, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and maybe we have more elements after that, but we don't have to keep track of everything at once. So, okay. There we go. So, let me at least save this so that it's so that if it crashes, we don't lose it. So, each of these elements is going to be in its own set, right? So that's the way we imagine it. 0 is its own set, 1 is its own set, 2 is its own set, 3 is its own set, etc., etc. And so what findSet is going to do is the goal of findSet is to give us return a representative of each set. And so remember when I say set, I mean the thing in mathematics that starts like A is equal to 1, 3, 6, and say B is equal to 2, 4, 8, or 2, 4, 9, I guess I typed. So the way to think about this, and then what does it mean to be disjoint? Right? Yeah, two sets are disjoint, or technically you can call them like, well, in probability you might call it mutually exclusive. When A intersection B, well, maybe I'll draw the intersection separately. Yeah, let's just use the math thing. Render, math, LaTeX. Cat B equals or nothing. So, and then of course it takes forever because it's actually compiling a LaTeX document. And there we go. Now I'll move this off screen, and we can go over here and find our little LaTeX. And so remember what the intersection means. The intersection means all the elements that are in common, right? So the intersection is defined to be A or X, such that X is in A and X is in B, right? So that's the definition of let's see if that did it right. Well, not quite. Let's put on some extra scare slashes. Is this one right? This one's better. So that's the definition of the intersection. So if A intersection B is equal to nothing, then that means that the number of things that A and B have in common are empty. And so that's how we can have these things called disjoint unions, because what we're doing is we're going to kind of combine these elements into sets, right? We want to put them together into sets. So the idea is we put the elements from our array into sets, and then we can always be assured that if an element is in one set, it's not in any other of the sets, right? Because that's what it means to be a disjoint set. So basically we want to group things together so that they're only in one category, and we want to be able to do that. And so here's the union function. So what is the union function going to do? Oh God, I shut that down. Not sure why so Discord's running. Maybe I'll stop that. I think my internet might be getting a little slow for once. It's not usually good doing that, but okay. So the union of two elements is basically what this means is you take the sets. Whoops. Well, I mean, I definitely taught this kind of stuff in Discrete. This is something I mentioned. Okay. Let's see here. Ooh, wow. I mean, I don't think this is going to help, but maybe it will. Okay. Okay, let me just see if refreshing this, it's what I always tell everybody else. If I just refresh it, maybe it'll be better. I'm sorry I've had so many technical issues today, but it's good that, I guess it's good that today is a kind of, it's still kind of blurry. Well, as long as I'm clear to everybody, okay, so let's do some examples, okay? So let me take all these numbers, and then let's just do some examples, okay? So the first example I'm going to do, and let's draw some circles. Let's union, say 0 and 1, okay? So then what I'm going to do is I'm going to draw a circle, and I'm going to put 0 and 1 into that circle together, right? And maybe 0 is the representative, and 1 is the just other element, so I'll put 1 over here, and I'll put 0 towards the top, so that 0 is the representative of this circle. All these other people are still in their own circles, right? They have little circles that we're not drawing in because there's just too many of them. So now let's draw in the union of, let's say we union 6 and 7, right? So then we create a new circle, and we throw 6 and 7 in there. Oops. And let's pick 7 as the it really doesn't matter. It's not important, like, the order of the elements. Let's just pick 7 as a representative there. And so these are the elements that are still by themselves. And now let's union, say, 2 more elements. Let's say we union 8 and 11. I know I've been unioning elements that are right next to each other, but that's not part of it. That's just me being random. Or being, I guess, non-random is really the issue. So if we union 8 and 11, now we put 8 and 11 into the same circle. Okay. So now, that's after 3 union operations. So now let's do one more union operation, which shows the power of the disjoint union operation. If we union, say, 1 and, say, 7. Okay? So now what you do is you look up 1 in your little array, and maybe this is an array of, say, pointers, and so the 1 is going to point, like the array that this thing is going to point to this element here, and then this element somehow is going to have to point to this element here. And so basically that's how we find out the representatives. And then we say, okay, now we're unioning with 7. 7 is the representative of 7, right? And so basically what we do is then if we have to union 1 and 7, we don't just union 1 along with 7, right? We don't put them in separate circles. What we actually do is we take these 2 circles and we join them together like this. So now there's not a second circle. So now 0 is the representative of the elements 1, 7, and 6. Since we haven't unioned 8 and 11 with anything other than themselves, they are still unioned with those. Now if you say run another union operation, so say we run union 2 and 8, then 2 will go into the circle, etc. Why is 0 representative? It's kind of random. All I'm saying is that you have to pick a representative. What does the circle represent in the actual code? Well, we're going to get to that. And there's no reason. Okay, if you insist, now 7 is the representative, 0 is just an element. Okay, now 0 is not the representative of that thing. Okay? It doesn't matter which element you pick as the representative, you just have to pick one of them, right? So here, 8's our representative, and 2 and 11 are just kind of sitting down at the bottom. 7 is our representative here, and you'll see why you need a representative in just a bit. Okay. So basically the idea of this is that it's a way to cluster objects. So how do we do this if we actually wanted to, say, implement this kind of thing, right? And so here's my hint to you. I've been drawing them as circles, but really you might actually want to draw them as some kind of tree structure. So here what we're going to do is you might draw something, let's put 0 back up as the representative, and then we have 7, 1, and 6 down here. So this is not exactly a search tree, but it is a tree structure in the sense that basically this is what you're going to do in terms of the code. And then this is what you're going to do in terms of the code for the other one. And so, yes. And now, the only thing that you have to worry about is exactly how to implement this. So you can implement it as something that has children pointers if you want to get all the elements out of a set, or if you want to be able to find the representative, you have to have a parent pointer. So basically when you go up in this direction here, let's see here. Let's see if I can make it cool. Yeah, like I want it to be that. When you go back up, this is the parent direction, right? So oops. What have I done? Wonderful. I broke it. The good news is I think we've got just about everything we needed out of it. So let's pull up CLion and let's implement a disjoint union. So let's make a new project. Let's call it Disjoint Union. Fall 20. Sure, a new window. All right. So what are we going to do here? Let's make a disjoint union class. I don't know. Where'd it go? Thought I was going to make a new class. Hang on a second. New class. There we go. Let's call it Disjoint Union. And let's create the header only because I'll implement this one as a template. And so in order to implement as a template, let's just do template class. Whoops, template. I'll use type name. Type name T. Cool. Why does it not like this? What's wrong? Expected unqualified ID. Not sure. So what if I change this to class? Does this like this better? Oh, I still I've posted a lot more code on GitHub. You know what the problem was? I misspelled template. That's why it hated me. So, okay, so let's decide what we have to do. So let's say that we have let's make a constructor. Let's make a, do we want to copy constructor? Sure. And remember, you need the T right here, reference, copy. What other kinds of things? We need the definite two pieces of thing that we actually do need. Let's fix this. The screen will go blank for just a second while I click this button. But you'll hopefully forgive me. Okay, there we go. And we want, let's see. Technically there's a make set, but we don't really need that. What we really want is we want a maybe add element. And then we can have an add element T, new element, like that. That's kind of like make set. And then we can have a union. Yeah, so let's say two elements need to be union. And then we want so this will return the representative, right? So this will return I guess we can put const on that maybe. So yeah, let's just see. Let us just see. Find set. Okay, there we go. And I guess that's really it. And then maybe we'll have a destructor. And I realize I've never shown. I showed some of the people this, but I didn't show everybody this. So maybe I'll do this. Let's include a vector and using a namespace std. And so I'm going to use a vector because I think it's probably the easiest way to. So we'll just have a vector of elements. Actually, I think what we need is we'll have to do it this way. So struct will have a union node, which also has a template type named T on it. And so what we'll do here is we will make a union node. And a union node is going to have some stuff in it, right? And so the stuff that it's going to have is a vector of union node pointers. And this is going to be called the children, I guess. And then we're going to, each union node is going to have a T value. So value, set value, and then basically that is what we are going to do. So now let's talk about the destructor on the union node. We're gonna make the destructor inside the union node. This way what we can do is we can say for node pointer in the children, we're going to do delete node p. And that's it. And then the destructor for this class is just going to be I guess we might get some double freeze if we do that. We'll worry about that in just a second. So, okay. So you notice here what I've done is this is actually a vector which is already using a template, but it's going to be the template is union node T, which is yet another template. So that's always a little bit annoying. Okay, so let's implement these three methods here, right? The important ones. I don't really think we need anything here. The vector should be of node, union node T pointers, right? So that's what this vector wants to be of, because, yep. All right. So now let's implement this stuff, and remember we just implement it right down here. We copy and paste the template construction onto each one of our methods. We then, what do? We then add, so here we'll have elements.pushback new union node T new element. That's it. That's all we do. So this function is pretty simple, right? Not much to do there. So find element. I guess here is, I know what to do for the destructor now. So remember I said we need a parent, and then I didn't put a parent in the node. So there we go, now we have a parent. And so now this will also be a way for us to tell if the node itself is a representative, because if the node is a representative, let me just put it in a comment here. If the node is a representative, then it won't have a parent. If it has a representative, it will have a parent. The end. That's it, right? So if the node has a representative, or if the node is a representative, then it won't have a parent. If the node has a representative, then it will have a parent, and that parent is either the representative or it's the child of the child of the child of the child of the representative, right? So the representative, the hint is that the representative is going to be the root of this tree that we make. Okay? So now if we want to union two things together, one way to do it is this. We're going to have to call find set. We'll have to maybe call find node, because and we'll have to write a helper here. Let's write a little private helper for find node. It's going to be almost identical to find set. In fact, find set is going to be the same thing as find node. The only difference is that this will return a union node T pointer, whereas the other one is going to return a just the element. Okay. Oh, and you know what I haven't added? There we go. That fixes that a little bit. There we go. There we go. There we go. Everybody's happy now, right? Okay, so what we're going to do here is we're going to say, let's say for so then we're going to say if the node's value is equal to the find element, and of course this is the one thing it needs, is it needs an equals operator. So whatever t is, it has to have an equals operator. Let's also check if node, so node shouldn't be none, but let's verify that, just in case, because that could really be something that would cause us some headaches. So then what we're going to do is we will return the node, and that's it, right? And then here we're going to return null pointer. So, okay. Now this is an O of n operation, so this is terrible. But there's a way to improve this search pattern. which is to use a hash table. If you use a hash table, you can get O of 1 searches here. And so then it's much faster. This find node would just be an O of 1 operation. So we're going to pretend like this is basically an O of 1 operation here, even though technically right here it's an O of n operation. As written, it's O of n. Because we have to all the elements to find a specific value. Okay, and I guess I shouldn't have used two different types of comments. I should have just done this, that. Perfect. Okay. So, all right, so this is a find. This is a stupid find. It doesn't really do anything very exciting. This one is not going to do anything very exciting. You know what it's going to do? We're going to find the node, find element, and we're going to call this union node. Come on. There we go. And then remember, this is supposed to find we want to find the representative here. So we're going to, basically what we're going to do is we are going to go up as far as we can via parents. Okay? So that's the idea here. We're going to go up as far as we can via parents. So we're going to say while pnode parent, pnode equals pnode parent, and then return pnode. That's it. We've just done find set. We've just done find node. We've done find set. We've done add element. Right? We're almost done. The only thing left to do is union. Right? That's the only thing we have left to do, is just unioning two things together. And so it's very exciting. Now let's union things, right? So at this point, the problem is we haven't made any tree structure. So now when we union two things, what we're going to do is we're going to set element 2 as the child of element 1's representative. Okay? So that's it, right? We're going to set element 2 as the child of element 1's representative. So we have to do find node twice. The first thing we're going to do is find element 1, and we'll call this node 1 equals this. And auto, remember what auto does. Auto is going to, it's kind of a, well, for me it's a new C++ feature. It's only 10 years old now. It's going to detect the type, so it's going to look at this and be like, the thing is a, maybe I'll just write it in. It's a union T pointer. So we could either use that or use auto. I prefer sometimes to write down the types because C++ is a beautiful language. It allows you to show the types that you're actually using. And so sometimes let's just do it. You know, no reason not to. Okay. So let's union these two things together, right? And so this is the climax of the whole story. This is the moral of everything in the universe. Right? So what we're going to do is let's get the representatives of both of these elements. Right? Here we just found the nodes. So we need to get the representative of both. Actually, we need to set element 2's representative as the child of elements 1 element. So first, we're going to say while node 1 parent node 1 equals node 1 parent. And then, even though it's a bit duplicative, we're just going to do the same exact thing for node 2, right? Don't worry about it. So actually, there's not really a better way because the problem is you don't know how many times you have to go up, so you can't really combine these two while loops. But now each one of these is the representative of the original node. So now they are the reps of the original nodes. And so now let us finish this thing. Let us just say node 2 parent there we go. And that's done. I think that's done. So this is it. This is a disjoint union. Okay? And so let's say the destructor here, I think it's going to be for auto p node in the elements, and basically if p node, and you'll see why I'm doing this in a second, if not p node parent, actually, you know what, we don't even need a destructor in the node. Never mind. We can just delete all the elements individually. And we don't have to do this, we can just say delete. So that's fine. Okay. Okay. Maybe we should make a display method though. So let's make a display method, right? Oops. Must have control all of that. So what should our display method do? Let's say for maybe we'll see out, and of course we'll have to actually include see out here. We'll have to include, there we go. What's the problem here? Oh, does it want me to say explicit? It does. Okay, so and then let's say if pnode.parent, then we can say cout has representative, and then we need to find the representative. So let's say all right, and then we'll end line there, and then else we'll say is a representative, and that way we'll be able to know. Okay, I think that should be fine. We'll see how this works, and now let's just add some code to main. So let's say and then include disjoint union, and now let's declare a disjoint union, and let's make it of integers. Okay, and so okay, so now we have our disjoint union. I guess the first thing we should do is see if the thing even builds. See what happens when you build it. Does it explode? It explodes. Wonderful. You'll see I'll never ever get a template thing to work with that explosion. What's the problem with it? It doesn't like this. So it doesn't like the constructor. What's the problem? What is the problem? Oh, the constructor was never written. So that's actually my fault. All right. Okay, so now let's say and then let's say while s is not equal to quit, right? And then let's say, you know, if s is equal to add, then we can input an integer, so cnx, or x is some integer, and then we can add the element x. Let's make sure that it's not actually already in there, so if not my union dot find set x, we'll do my union dot add element x. What's wrong with you? Instantiation of member function cannot initialize return object of type int with L value of type blah. Interesting. Interesting. Find set. Oh. Right? Is that the problem? Why does it still not like it? In instantiation of blah 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 cannot initialize object of type int with L value of type union blah 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 blah. Let's look at the declaration up here. No, it's still right. Huh. I am honestly not sure what it. I mean, it should be obvious. There should be something really simple that I'm just not seeing. But yeah. Why does it hate me? Okay. Oh. It doesn't hate me. Huh. Look at that, it actually worked. So that's very strange, right? That shouldn't happen. Okay. So let's see. And then we can say my union dot find set. And yeah, the represent, I guess. Is, there we are. And then I guess we can do one more, else if s equals display, then we'll call my union display, and else if, and then here's the important one, s equals union, we will cn x, cn y, and of course that doesn't exist yet, and we'll do my union dot union. Or maybe we'll just display it after every operation, but you know what, we can display it anyway. Okay. Okay, and now we just have to declare the integer y. And I think now we just have to input s at the end to prevent an infinite loop. And now I think we can run this thing, right? Maybe we should say enter command. That way it'll be obvious that we're at that prompt rather than just nowhere, because it's kind of going to look like nothing if we don't have it. Okay, so let's do this. Let's hope it doesn't explode. So now let's add 5, I guess. Oh, it exploded. So just adding the first element caused it to detonate. So either finding the set caused it to detonate or this caused it to detonate. And so why did finding the set cause it to detonate? Find node. That should be okay. This one should be okay, right? I'm disappointed. I thought at least this was gonna work. I mean, I'm just pushing something back into an array, right? It's not like I'm doing rocket science here. So is it this? Let's see out element has been pushed back. And that'll tell us if that's the problem, but I don't think it's even getting there. I think it's dying inside of find set. So let's say here, find node is almost done. Oh, but there is no node. So if not p node, return. Unfortunately, we just have to return a default T constructor, which is terrible, but whatever. Let's just return invalid, and so invalid is going to be something we do in the constructor. So T invalid, and then we'll just say there we go. And then we'll add it to here, so we'll have T. This is just an element that we will never add. So new element is not equal to invalid. Right, so don't add the invalid element in there. So maybe we'll make the invalid element like -1 or something. That way we know for a fact that there's no -1s ever as objects in this thing. Okay, so let's see if that dies. So add 5. Okay, didn't display though. Okay, let's try again. Add 5. Display. Okay, why is display not working? I thought display would output things. We have a bunch of COUTs here. Am I just dumb? Why is this not working? Why is this also not working, right? Okay, so it's doing something. Oh, hey, I think I know if element is not equal to invalid. No, that's right. That's right. Okay, help me out. I'm confused. Why wouldn't this be working? Because, oh, it's never actually pushing the element back. So I guess new element was equal to invalid? But how can that make sense? Let me think. If element is equal to invalid, then it won't do this. But that's what I want. Notice that it's actually, when I say add, and then I do 5, see, it's not actually pushing anything back. Okay, so let's look at the find set again and see what I've done here. So, okay. Okay, so this will be invalid equals -1, and then we'll do int invalid. Okay. There we go. Yeah, I never actually add the element, so I think we're almost there. I think mostly it's been mega stupid stuff. So let's keep that one in. just so that I'm pretty sure it's doing something. It's always nice to be sure it's doing something. Okay, it didn't do anything. Oh, wonderful. Come on, stop making stupid mistakes. This is where, like, this code, I think, primarily works. I just have to, like, not do something abysmally stupid in the next 10 seconds, and it should run fine, but... See, it's just not adding anything. So it's not even running, it's, like, not even running this code. So, why is it not running this code? So it's, if s is equal to add, we're going to print cout, hello there, we are here now, just to double check that we're there, and then my union.findSet is not equal to invalid, right? Oh, we want it to be equal to invalid. We want it, abysmally stupid. Right? Because if it's in there, then we don't want to add it again. I just don't want duplicates. I just don't want duplicates. Like, the whole thing, this is not even the data structure. I just don't want duplicates. Oh, there we go. There we go. You see, 5 is a representative. Now we add 10. And now we add 13 for no reason. Add 7. Oh, look at this. And you see that they're all representatives of their own little classes. And now let's try to add 13 again. And you see it doesn't. Ha! That was the point of all of this. None of this actually has to do with disjoint unions. It only had to do with me trying to get every element represented uniquely. And so that was primarily stupidity. Okay, so let's get rid of this cout stuff. So, as it turns out, I think I used the end key too much because my end key has been fighting me pretty hard. Sometimes it works at a rate of about 70%, which means that it's not very good. Okay, cool. Now let's rerun the program. All right, let's do add 5, add 10, add 15, add 20, add 13, add 7, add 255. Okay, so now we have a bunch of nodes in here. And so now let's try our thing, all right? Our thing is going to be to union, let's say we're going to union 15 and 7. All right, hit it. So notice that 15 is a representative and 7 has the representative 15, right? So that means that 7 and 15 are now grouped together. All right, now let's add another element. Let's add 77. And so now let's union 77 and 7. And so let's see what happens. Oh, I guess, oops. I guess now I was setting the parent backwards. So if you notice what happened here, 15, oh, it's because this one was, no, I'm not. I didn't set the parent backwards. This is correct. This is correct. This is just not, this is the opposite order of what I meant to do. You notice here, 15 has the representative 77, 7 has the representative 77, and 77 is a representative. Okay, so what that means is that you have one group, this one, and this one. And now let's union some more stuff together. Let's union 5 and 10. Let's union 10 and 20. And so notice here that 5 is a representative, 10 has the representative 5, and 20 has the representative 5. So now let's do what everybody wants to do, which is say union, let's say 10 with 7, right? And so the point here is that if this is all going to work out correctly, then everybody's representative should either be 77 or 5. And I'll show you why or everybody's representative should be 5, but the parent can either be 77 or 5. Let's hope that happens. Okay, so why did that happen? So it happened because Yep, so that happened because what happens is that it'll try to union 10 together with 7, and 7 was in the 77's group, right? 77 was team captain, and here 5 was team captain of this group. But now that you've unioned them both together, if you go back up all the way to the parent, like the root of this tree, then you'll see that 5 is the team captain of the whole big team now. The only elements that are not together, right, are 13 and 255, so they're lonely. So let's union 13 and 255 together. And so then let's add a new element. 34, add 45, add 56, add 67, right? And then we can union some more elements together. So let's so if we union, let's say, 5 and 67, then it's going to be the simple operation because 5 is going to become the parent of 67. But if we do something kind of backwards where we union together, say, 5 and 56, or 56 and 5, remember, everything is going to become the child of 56. So now 56 is going to get to be the team captain, and 5 is going to be the child of 56. So that's how a disjoint union structure works. And you see that it's able to basically maintain these groups like this. So yep. Cool, right? So 65 has multiple children. 56 has multiple children. I think that 56 has 5 as a child, and then everyone else is a child of 5, if you know what I mean. So basically, this is only showing you, remember what this is doing to get the representative. This is going all the way back up in the tree. So what I could do here, let's do it like this, so we actually see it a little bit better. Okay, let's do this. And now let's rerun this thing. So let's quit to make sure quit works. Oh, look, it worked. And now we have a failure. What's the failure? Disjoint union. Wow. Look at all those errors for a missing semicolon. Okay, so let's add 5 again, add 10, add 12, add 15, 17, 20, add 22, 24. I'm just adding a bunch of elements, right? 34, 44. The numbers don't even really matter, right? It's just that they just need names. Add 67, add 1729, of course. All right, so I think that's enough elements to add. So now let's union together some things. So let's union 17 together with 67, or 56, or 67, I guess. So now we have the parents in there too. So it says 67 has parent 17 and representative 17. And now we can union together 15 and 17. So everybody is currently, right, so basically, let's see. So 15 is the representative. Here 67 has the parent of 17, and 17 has the parent of 15. So that's how the tree works. If we now union together, say 34 and say 67, what's going to happen? So the point is, oh no, we want to do 67 and 34. I think we want to do it that way. The reason why I wanted to do it this way was because now you see that what our algorithm does is it finds the root. It doesn't make 34 the child of 67. it makes 34 the child of 67's representative. So you see that 34 has a parent of 15 and a representative 15. 17 has a parent 15 and representative 15. And 67 has a parent 17 and representative 15. And so now let's union some more stuff together. So let's union together 5 and 10, union 10, 12, union 12 and 15. And so now let's union together 15 and 34 and see what happens. So I think what's going to happen is that the thing that is the I think 5 are our parent representative of oh, that's funny. This one has a different parent, but anyway. So let's do it. Actually, let's do 17 because they're all in the same group. Uh-oh. Bad things happen when that happens. Let's see. 17, 34. Oh my. This really screws up the input. Sorry about that. So we'll union together some stuff as usual. So 45 and 56, union 67 and 45, union 5 and 10, union 5 and 22, union 5 and 34. And now if we union together, let's say 34 and 45 maybe? Yeah, 45. Let's see what happens. So now it looks like everybody has representative 5, but whose parents have changed? So we see that 67 was the representative, right? Because 45 and 56, basically 45 was attached to 67, 56 was attached to 45, and now 67 is the top. But now everybody has representative 5, except for 5, who has no parent. And we see that they still have different parents, right? Like they never lose their parents. So that's the way to think about it. So there is an optimization that you can make to this. Okay? So the optimization you can make is actually in the union algorithm. So what you can do in the union algorithm is basically you can remember all of the nodes that you traversed on your way back up to each parent, and then assign them. You can reassign their parents. So because think about the inefficiencies that can occur in this data structure. The main inefficiency that can occur is the problem which happens when you basically get a long chain. A is the parent of B is the parent, or I guess A is the parent of B is the parent of C is the parent of D is the parent of E, right? It's the same problem that you get with general binary trees. Which is that in a binary tree, if you have just a long linked list looking structure and there's not a lot of other children, then the problem is that's an O of n search to go all the way down to the height of the tree. And so the same problem kind of occurs here. So this can be an inefficient algorithm, except that there's an optimization that I might show you guys next time, where you basically, as you're going up, if the parent isn't the representative, you just assign the parents as you go up to be the representative. And so what that does is it takes any kind of long chain structure, and the first time that you search through that, right, the first time you search through all those nodes, you just pop each node up to being right under the representative as the second level in the tree. And so what that does is it vastly decreases the inefficiency of the structure. And so basically every operation then, any search operation to find the representative, all these while loops, they either become O of 1 because you only have to search once, or technically you could be at the representative so you don't even run it. So it's O of 1 operation, or alternatively, during the next union, it will be made an O of 1 operation by just kind of relinking all of these things up until they're just all connected to the representative. So basically, this thing would not have happened. Right, this 45 connected, or I should say 45 connected to 67 connected to 5, like that wouldn't have happened, and 56 connected to 45 connected to 67, connected to 5. Those things would not have happened because as it was unioning back up, it would have relinked all those elements. So that's the disjoint union structure. It's kind of an interesting data structure. It's basically a tree structure, right? That's all it really is. It's just a creative use of a tree structure. But I think it's a kind of interesting data structure, and so it's something that we'll talk about. And then maybe next time we'll talk about tries. I think tries are probably on the schedule for next time. We'll talk about those because they're just another tree structure that isn't exact. It's not a binary search tree. It's not an AVL tree or not a red-black tree. It's not a heap. It's a different thing, right? It's a different way of thinking about data. It's a different way to store data based on the needs of the moment, right? Because you notice that a binary search tree can't do this, right? This is not something a binary search tree does, but this is something a disjoint union does, right? It keeps track of basically clustering of elements. So if you cluster this group with this group, now they're the same group. And so the one problem is obviously there's no way to go back. You can't separate two groups. That's like an O of N operation because then you have to decide each element. Do you go into group A? Do you go into group B as you do the separation? Anyway, I think that's it for today. I did intend to kind of get to tries, but of course the good news is that I made so many errors in my cout. It was mostly in my outputting and my invalid thing. Literally all of the problems in this code came from the fact that I just didn't want to have, and you see now why I didn't want to have duplicate elements, because duplicate elements would cause a problem. If you had 5 and then again here you had 5, then because we're using the value of these things to search, it would never find that further on 5. It would always find the first one, and then it would always link to that one, and the other one would just kind of become an orphan. So that's why I wanted to do that. I was trying to make it nice, but I ended up making it just way more complicated and buggy. But I think it's all fixed now. So anyway, that's all for today. I think I have to go and talk to somebody now, so I'm going to let everyone go. All right.